The final section in Chapter 6 deals with standard enthalpies of formation. The standard enthalpy of formation is abbreviated delta H sub F. The delta, remember, is a change, so we're talking about a change in enthalpy. The degree symbol signifies that it's a standard enthalpy change, and I'll talk more about that in a second. The F is, we're talking about the formation, so F means formation. And this delta H deals with the production of 1 mole of compound from its elements in their standard states. And again, that's where the degree symbol comes from. The standard enthalpy of formation is 0 for elements in their standard states. And typically standard states refers to 25 degrees Celsius, 298 K, 1 atm, and 1 molar. So let's look a little deeper into that. For a compound, for a gas compound to be in its standard state, then its pressure needs to equal 1 atm. If we're talking about a solution, then its concentration needs to equal 1 molar. So for a solution, the concentration needs to be 1 molar, and it needs to be a pure substance if we're talking about liquid or solid. If we're talking about an element, then it's in its standard state when it's in whatever form it would be in at 1 atm and 25 degrees Celsius. So for example, for nitrogen, that's gas, and potassium, that's solid. Now, when we're talking about the overall enthalpy of formation, it takes into account the enthalpies of formation of all the individual species that are contributing to an overall reaction. So, I know this might look a little intimidating, but let's walk through it. If I had a reaction where I was combusting methane, that's CH4, then the equation would be methane plus oxygen is going to give me CO2 and water. And if we were to break that down into the individual steps, then we could get a little bit more information. So starting with the reactants, we have methane, that's CH4, and if you look at step 1A, you can see that the change in enthalpy for methane going from CH4 to its individual elements, that's carbon and 2 sets of H2, then that would require 75 kilojoules of energy, right? We're going from methane to its individual elements. That needs energy put into it to break apart those bonds. And if we look down at step B, when we're going from reactants to products, we don't need to break apart the individual oxygens at this point. So there is no change in energy going from the reactants to the elements at this point. Now if we look at the element stage, we have methane that's going to combine with we have carbon that's going to combine with 2 of the oxygens, and that's going to form CO2. And you can see at step 2C, the amount of energy that is released when that happens is negative 394 kilojoules. So that is the formation from adding carbon to oxygen to make carbon dioxide. And it's negative because energy is released when that process happens. If we were to look at step 2D, we would see a couple of things are happening there, but we have the oxygens and the waters that are combining to form, we have the oxygens and the hydrogens that are combining to form water, and the energy for that reaction is negative 572 kilojoules. Now, if we were interested in how much energy is required for the total reaction, we could sum all the individual parts up and to see what happens. Now, one thing here is that the way that we get at the total energy enthalpy change in a reaction, it is done by calculating the sum of the enthalpy changes for the products and subtracting the sum of the enthalpy changes for the reactants. And I will give you an equation for that in the next slide. But the example here, just to walk you through it, the reason why, number one, there's a negative sign at the beginning is because this is for the reactant stage. And if you remember, I told you we take products and we subtract reactants. Also, it's a negative 75 kilojoules, and that is because we're talking about the formation of methane. And the formation of methane would be going in the opposite direction where you have carbon and 4 hydrogens coming together to form CH4. So if we were going in the opposite direction, then in this image that's here, carbon plus hydrogen giving us CH4, then that would take negative 75 kilojoules of energy, or energy would be released. It's 0 for the formation of oxygen, as it will always be when you have an element in its standard state. And then we're going to add the formation for the products. So we have the negative 394 kilojoules, which is the formation for CO2, and we have negative 572 kilojoules, which is for the formation of water. And that will give us a total of negative 891 kilojoules. So let's walk through a little bit more detail on solving problems like this. First, if you are reversing a reaction, then the magnitude of delta H will remain the same. So that means the number is the same, but the sign will change. And also, when you're doing an enthalpy calculation, one of the things you have to make sure is that the equation is balanced. And when you have a balanced equation, anytime you have an integer in front of a compound, you always will need to multiply delta H by that integer. The change in enthalpy for a given reaction can be calculated using something called Hess's law, and this is what I mentioned in the previous slide. The delta H for the reaction is going to equal the sum of the delta H's for the products minus the sum of the delta H's for the reactants. Now these N's for products and N's for reactants is just reminding you that you must multiply the individual heats of formation for the products and reactants by whatever integer is present in the balanced chemical equation. The final thing here is elements in their standard states are not included in the delta H of the reaction because their formation in their standard state, the heat of formation in their standard state is 0, meaning they're already in that state, so it doesn't take any energy either into or out of to put it in that state because they're already there. So let's look at an example. Problem says calculate delta H, and that should be for the reaction, of sodium and water giving sodium hydroxide and hydrogen gas. And we are given the following information. So we're given the heats of formation of sodium, and then this is sodium in its standard state, which is solid. So you can see that the heat of formation for that is 0. The heat of formation for liquid water, negative 286. The heat of formation for sodium hydroxide, negative 470. And the heat of formation for hydrogen gas, which is in its standard state, and that is 0. Now, if there's a moment of panic thinking you need to memorize these things, worry not, friends. There are tables of information that give you the heats of formation, including things like sodium, solid sodium, and hydrogen gas. So these are not something that you have to memorize. They will either always be given to you when you're trying to do a problem, or you will be given a sheet of all of the standard heats of formation. You just have to understand what to do with them. The first thing that you do for them is the Hess's law equation, where the delta H of the reaction is going to equal the sum of delta H's for the products minus the sum of delta H's for the reactants. Now, what would that look like? You can pause it here and try to calculate it before I show you. If we were going to sum the delta H for the reactants, we would do it like this, where we would have 2 times 470, because if you look at the balanced equation, you can see you have 2 sodium hydroxides, and the heat of formation for sodium hydroxide is negative 470, so you have 2 times negative 470, and then you would be adding the heat of formation for hydrogen gas, which is 0, and then we subtract the heat of formations for the reactants. The first reactant we have is solid sodium, which is 0, so we have a 0 there. And then we have 2 times negative 286. Remember, if we look at the balanced chemical equation, we can see we have 2 waters. So we have to multiply the heat of formation of water, which is negative 286, by 2. Doing so will give us an overall change in enthalpy for the entire reaction, which is negative 368 kilojoules. And that, friends, ends chapter 6.